Space is the final frontier, and robots are the vanguard of our human explorations of the universe. So what's it like to be a robot in space? Well, you have to contend with micro or zero gravity. You have a lack of oxygen and water. You have the vacuum of space and the very different atmospheres of other planets. You're exposed to extremes of cold and heat, and you have to bring with you a completely autonomous supply of energy. You have communication delays and limits. Now, these same challenges face humans in space. By sending robots before we go, we learn how to overcome these limits before we put our lives on the line. Robots carry sensors and instruments that allow us to understand where human missions might land, where we could mine water or other chemical compounds, and make preparations for deep space forays. But perhaps the biggest challenge in space robotics is distance. If a robot breaks, we can't just go fix it. To increase the chances of success, robotic systems need to be hardened in an engineering sense to withstand those extremes and made robust to avoid catastrophic failure. With space missions, we push the extreme of working remotely with and through our robots. Robots in space use many of the standard robotics solutions that we've developed for robots here on Earth. The rockets that push our payloads out of Earth's gravity well have inertial guidance systems akin to the automatic pilots we've seen in robotic planes. The probes that chart the moons of Saturn shoot pictures in a remote-controlled dance with humans at mission control, like that guides our unmanned aerial systems here on Earth. And the rovers that scour Mars for signs of life use navigation systems like those we use on wave-gliding robots in the Pacific Ocean. Nearly all transportation in space is carried out by robots. Robots in space include rockets, spacecraft, shuttles, satellites, probes, landers, and rovers. On board shuttles or space stations, we also find manipulator robots and humanoids. Much of the work in space robotics has focused on low Earth orbit and the surfaces of other planets, so we'll focus on those things too. Now, the most exciting project in orbital robotics is the International Space Station. Hello, microgravity. Here's where humanoid robots are being developed to help humans work inside the space station. Robonaut 2, or R2 for short, arrived on the International Space Station in 2011. R2 is shown in this picture with NASA astronaut Dan Burbank. Now, like Baxter, R2 is built to interact safely with humans. It consists of a head and a torso with two arms that function independently. Robonaut 2 can be controlled by a human operator in the space station who wears a glove and a headset, or it can be remotely controlled by ground control. And R2 can also be programmed to do some tasks autonomously. Now, many of its low-level operations, like grasping control, are done autonomously, even if, for example, the object to be grasped is determined by its human operator. How can Robonaut 2 help humans in the challenging work conditions of microgravity? Why bother to have a humanoid in space? Well, inside the space station, R2 could set up an area for the manipulations that only humans can do, help set up an operation. And during an operation, R2 could assist by providing tools or holding something in place, and then it could clean up afterwards. Now, NASA plans for Robonaut 2 to work on the outside of the station as well, where conditions are extremely harsh. At the Earth's distance from the Sun, like the International Space Station, temperatures in sunlight can rise to over 120 degrees Celsius, or 248 degrees Fahrenheit, well past boiling for water. But on the side of the craft not facing the sun, heat radiates away so quickly that temperatures on the dark side can sink to negative 100 degrees Celsius or negative 148 degrees Fahrenheit, well below freezing. In space, no one can hear your equipment freeze or boil. Since it takes about 90 minutes for the space station to orbit the Earth, if R2 were working outside for a few hours, it could easily encounter those extreme temperatures. Without thermal control, R2 would likely suffer a number of problems, including camera and battery malfunctions. Robonaut 2 would need to be outfitted with an array of passive thermal control, such as insulation and external coatings, and active thermal control systems, such as electrically powered heaters and coolers. Once thermally hardened for work on spacewalks, R2 will be able to replace humans on these dangerous external tasks. One of the reasons to design R2 as a humanoid is so that it can use the same tools, handholds, hatchways, and equipment as humans do. And this is why each hand of R2 has 12 degrees of freedom. Amazing hand dexterity. Robonaut 2 can use that manual dexterity to do things like pick up a space blanket. Robonaut 2 can also use its dexterity to communicate, to sign in American Sign Language. Part of Robonaut 2's great ability to reach and grasp and interact safely comes from the touch sensors that it has on its hands. These sensors provide R2 with feedback so that it can hold on to very fragile objects or to apply stronger force when needed. Robonaut 2 is also strong. It can lift a 20-pound weight and can do things that humans can't, like hold that 20-pound weight with an arm outstretched for long periods of time. Robonaut 2 has been designed to be compliant, like Baxter. It knows when it has encountered an unexpected object and will shut down immediately. This makes R2 safe to work with. Robonaut 2 also has a vision system. It can pick up an envelope and examine it, and this function involves rudimentary object identification. Even though Robonaut 2 only works inside the space station at the moment, other robots are at work outside. They are all versions of arm-like robots that remind me a lot of the pick-and-place robots that we see at work in factories. The first of these outside outer space robotic arms was the so-called Canadarm. Its real name is the Shuttle Remote Manipulator System. Built for the space shuttles by the Canadian Space Agency, the remote manipulator system was teleoperated by crew members through a computer interface. The remote manipulator system turned out to be a real workhorse for the whole shuttle program. In 1997, the Space Shuttle Discovery serviced the Hubble telescope, and this involved picking the telescope from its orbit and then placing it into the payload bay of the shuttle. Once the telescope was safely in that payload bay, astronauts could spacewalk to install new instruments. What NASA quickly figured out is that they could use the remote manipulator system to actually move astronauts around on spacewalks. I think maybe if you're going to do that, you should call them space reaches. Now, after the Columbia Shuttle disaster in 2003, the remote manipulator system was mounted with an extra long bone, if you will, a long boom, that used an extension that allowed it to hold a camera underneath the shuttle to view the heat shielding for damage. The remote manipulator system proved to be incredibly useful, and it spawned the creation of Canadarm2 for use on the International Space Station. What's really cool about Canadarm2 is that it assembled the International Space Station. See why we need robots in space? So, how does Canadarm move around? First of all, the Canadarm sits on the mobile base system, which allows Canadarm2 to move around on a track, giving the whole system a translational degree of freedom. A second way that Canadarm2 moves around is end over end. It can grab onto a fixture that provides power and computer control, and then it unhooks the end that used to be the base. So Canadarm2 does cartwheels. Acrobatics like that are facilitated by the microgravity of a low Earth orbit. The effect of constant free fall in orbit is that objects are nearly weightless. So the Canadarm2 can move its mass around with much smaller motors than it would need for the same gymnastic routine on Earth. Canadarm2 also has more automated behavior modules than Canadarm1 did. Canadarm2 has automatic collision avoidance, automatic vision feature for grabbing free-flying payloads, and force movement sensors that provide it with touch-like sense. Having built the International Space Station, one of the main jobs of Canadarm2 is to grab, dock, and unload unmanned spacecraft that deliver vital supplies. Canadarm2 has the ability to perform finer scale manipulations by adding onto its end a two-armed robot called Dexter. Dexter is loaded with many degrees of freedom, allowing it to swivel, pitch, yaw, and grasp. Now, what's really neat about this combination in robotics terms is that Canadarm2, which is a robotic manipulator, can use as an end effector another robotic manipulator, Dexter. So hanging onto and moving around another larger robot is made possible because of the near weightlessness of being in orbit. Dexter is used along with Canadarm2 to change batteries, replace cameras. These are jobs formerly done by astronauts in long, tiring, and dangerous spacewalks. Dexter is built specifically to work on the International Space Station. Dexter itself has a toolkit from which it can select different end effectors, and different graspers are built for different jobs. Now, one important job is to replace failed circuit breakers that are part of the station's electrical system. Dexter can manipulate the circuit breaker box, remove the failed circuit breakers, and replace them. Then Dexter can put its end effectors back in its toolbox. Robonaut 2, Canadarm1, Canadarm2, and Dexter are all designed to help humans grasp and manipulate the world. Whether located on a shuttle, crawling around the outside of the space station, or hanging out inside, they all operate as nearby extensions of our own arms and hands. These robots are all examples of work in orbital robotics. The other major field of space robotics is that of interplanetary robotics, whose stars are the planetary rovers. Unlike robots in orbit around the Earth, robots on other planets are separated from us by both long distances and long lag times in communications. But the robotics challenge is not just about how to communicate with your robots, but how to control them over long distances for the purposes of virtual presence and virtual agency. Presence and agency are essential for us as scientists and explorers, and for being able to adjust the original mission as new information reveals faulty assumptions, or the robots have problems, or we have an increased understanding of what the planet is providing in terms of challenges and opportunities, and so we create new tasks and goals. Twin robot rovers, Spirit and Opportunity, were built to study the complex geology of Mars. Their primary goal was to understand how the activity of water on Mars influenced the planet's environment over time. Thus, the Mars exploration rovers are part of NASA's long-term mission to follow the water and achieve 4 scientific goals that extend across multiple missions and into the future. The first goal is to determine if life ever arose on Mars. The second goal, characterize the climate on Mars. Goal number 3, characterize the geology of Mars. And finally, prepare for humans to travel to and explore Mars. Now, the Mars exploration rovers are a watershed moment in space robotics. The incredible success of this mission has set a new standard in space robotics for planetary science and exploration. Because of their scientific tasks, Spirit and Opportunity are often characterized as robot geologists. 4 teams of humans on Earth guided the geological work, which falls into 4 categories: mineralogy and geochemistry, soils and rocks, geology, and atmosphere. Early on in the mission, these 4 scientific teams met daily to discuss the latest information from the robots and then create a new plan for the following day. Here's what's really cool. Those plans were then uploaded via radio to each rover. The rovers would then autonomously enact the plans and then report back. And what's really nifty about this process is that scientists at Mission Control were reprogramming the autonomous robotic rovers every day. Now, contrast this with real-time remote control, where instead of a plan enacted in computer code, scientists have the plan in their heads, and they directly control direction, speed, and any instruments by inputting commands manually. Now, here's the problem with real-time remote control for robots on other planets: delay. Radio waves, laser pulses, however you want to communicate, can only travel at 186,000 miles per second, around 11 million miles per minute. That's the speed of light. So any command you send to Mars takes a minimum of 10 minutes to reach the rover, plus 10 more minutes for the rover to respond. And that's the good news. 10 minutes one way is when Mars and Earth are only 110 million miles apart. The bad news is that that delay can almost double to 18 minutes when the distance between the two planets grows to 200 million miles. Because of these communication delays, NASA decided early on in its planetary exploration programs in the 1960s to avoid any attempts at real-time remote control. Now, autonomy for planetary robotics comes in two flavors. One type is fixed autonomy, where the programming that controls the interactions of sensors and actuators is fixed. It's not reprogrammable. The other type NASA calls batch processing, but I think it's better described as reprogrammable autonomy. So reprogrammable autonomy is the type employed in Spirit, Opportunity, and Curiosity rovers on Mars. The idea here is the one we just talked about. Every day a new program, a new plan is uploaded to each rover. Now, the trade-off with reprogrammable autonomy is one of adaptability versus time. If you can reprogram your robot every day, then every day it can do something new. It can adapt to the information it discovers and any unforeseen changes in how it's operating. However, it takes time to reprogram, to evaluate what to do next, and to communicate those plans. So robots with reprogrammable autonomy, compared to those with fixed autonomy, may need more time to accomplish a given task or mission. Better understand this trade-off, we need to look at the other challenges with communication. Not only are there delays that make remote control difficult, but the windows for communication are limited. Time intercedes here from a different angle. First of all, the two orbiters, Mars Odyssey and Mars Global Surveyor, relay the signal from Earth to the rovers, but they only have communication for 8 minutes with each rover per Mars day. In that time, about 8 megabytes of data can be transmitted to an orbiter. 8 megabytes, by the way, is about the size of a high-resolution image that you might ordinarily send as an attachment on an email. That sample of 8 megabytes of data then takes between 1.5 and 5 hours for the orbiters to send back to Earth, which receives the signals on the deep space network of antennae. Another part of the communications breakdown is that the rovers only have enough battery power to transmit for 3 hours a day. Moreover, even if they could broadcast continuously, the lines back to Earth would be busy. The deep space network has multiple clients, namely all of the spacecraft that NASA has flying outside of Earth orbit. Whew. So, in summary then, interplanetary communications, which happen in both directions to and from Mars, to and from the robotic rovers, are delayed, are of short duration, and have to be of small size. When we speak of communication, we learn the importance of the robot's energy supply, which powers the radio transmitter and the receiver. Spirit and Opportunity have 2 rechargeable lithium-ion batteries and a solar array to charge those batteries. When under full sunlight on Mars, the solar array generates 140 watts at 14 to 18 volts for up to 4 hours. Driving the rover takes 100 watts of power, so travel can be accomplished in sunlight using the solar panels. 6 wheels, each with their own motor, are power the forward motion. Top speeds of about 5 centimeters or 2 inches per second, about 1/10 of a mile per hour, can be reached. Space turtles, watch out. Now, the battery system has a capacity of 15 amp hours at 12 to 16 volts and is used for communications and nighttime operations. Batteries can also be used to heat the temperature-sensitive electronics during the cold nights and the Martian winter, but the primary heating is provided by 8 radioisotope heating units, which by radioactive decay continuously generate 1 watt of heat. All of the sensors and instruments on the rovers also require energy, so their use has to be carefully planned and scheduled. A host of cameras are mounted on the mechanoid body of Spirit and Opportunity. On top of the mast sits a dual camera system for 3D panoramic shots of the landscape. They rotate 360 degrees and swivel up and down. Located on the arm of the rover is a microscopic camera that can take close-up shots of surface materials. And 6 other cameras use power and are used for navigation. 4 wide-angle cameras are located on the body of the rover and are used to detect navigational hazards like cliffs and large rocks. 2 navigational cameras are mounted on the mast alongside the panoramic cameras and are used in path planning. So these 8 cameras are the primary sensors for giving scientists on Earth virtual presence through the rover. So vision is a very important means of perception for geologists. Layers of rock indicate sedimentary action usually caused by wind or water. Valleys can indicate erosion or glacial movement. And colors of rock or sediment can give clues to mineral composition. Now, during their first 4 years on Mars, the rovers each averaged 25,000 pictures per year. Spirit and Opportunity have created an incredible catalog of images that really do make you feel like you are there, present on Mars. 3 scientific sensor systems, all of which are spectrometer instruments, look for water, iron, and chemical composition. A spectrometer measures the properties of light that are emitted or reflected or transmitted by objects or reactions. How that light changes as it interacts with the material tells us something about the composition of that material. Looking for signs of water, and located at the bottom of the mast is the miniature thermal emission spectrometer, which analyzes the infrared light reflected off of objects. This instrument looks for carbonates and clays and minerals formed by water. Now, looking for iron-bearing minerals, the Mossbauer spectrometer is located at the end of the rover's arm, so that the head of the sensor can be placed directly on the soil or the rock. Analyzing the composition of elements, there's the alpha particle X-ray spectrometer, and that's an active sensor. It emits alpha particles that reflect off materials. The alpha particles create X-rays as a byproduct of their interaction with the material. The patterns of the returning alpha particles then indicate the elements that make up the material. Like the sensor head of the Mossbauer spectrometer, the sensor head of the alpha particle X-ray spectrometer is located at the distal end of the rover's arm. Now, the main electronics of both the sensor systems are located in what's called the warm electronics box, the heated main body of the rover. A 4th instrument is on the robotic arm and hand, and it's an actuator, an end effector called the rock abrasion tool. This tool grinds and abrades the surface, creating a shallow hole about 2 inches in diameter. Now, getting below the surface, any hard rock allows for analysis by the other instruments on the hand. Action enhances perception. Now, what makes it possible for these instruments to do their jobs is the arm, or what NASA calls the Instrument Deployment Device. The rover's arm has 5 degrees of freedom. The joints of the shoulder, elbow, and wrist are all revolute joints that rotate. The shoulder has 2 joints oriented perpendicular to each other. The elbow has a single joint, and the wrist has 2 joints. As the wrist rotates, it brings different instruments on the hand to bear on the soil. The Mars exploration rovers have met and exceeded NASA's expectations. Originally designed for a mission of 90 days, Spirit sent its last communication in 2010, 6 years after it began operations, and traveled nearly 5 miles. Opportunity operated for over 10 years and logged 25 miles. Scientific achievements of the mission have been many. Spirit took movies of swirling dust devils, found circumstantial evidence of water by detecting sulfate minerals, and found silica deposits that indicate a much wetter past. Opportunity found evidence for water over a wider range of terrain, indicating a past with large bodies of standing water. Now, Opportunity landed in a dry lake bed, so its first major discovery was of the mineral hematite, which typically forms in water. That was followed by finding brightly colored gypsum created in veins, likely by flowing water. Now, this is just awesome. Robots as our mobile, reprogrammable science laboratories I can't help it, but it's like nerd goosebumps, right? This is seriously cool stuff. Spirit and Opportunity are two of my all-time favorite robots. In spite of this excellent work and amazing robustness, things did go wrong, and those failures are informative about the challenges of facing robots in space. One of the biggest problems encountered early on was that the solar panels got dusty, really dusty. Remember, there's no surface water, so the dust is extraordinarily dry. Static electricity builds up worse than on a cold winter day, and all that electrostatic dust is attracted to the electronics of the rover. Now, the team anticipated this problem in the design of the mission, and they were right that it would be a problem. Dirty solar panels resulted in a reduction by 50% in the power supply. This is the kind of problem that only gets worse, right? The dust and dirt continue to collect. In 2013, a Chinese robotic rover, U2, sent to the moon, ceased to move 2 months after arriving. While it's not completely known why U2's motors stopped working, the China National Space Administration concluded the problem was likely electrical and likely caused by cold damage in the long lunar night. Remember that a single night on the moon lasts 2 weeks, and U2 failed to restore movement after its second lunar night. In the face of environmental challenges like dirt and cold, a reprogrammable rover offers the possibility of at least trying to come up with a solution. What the mission engineers for Spirit and Opportunity recognized is that the winds on Mars could be used for cleaning the solar panels. For example, over a 1-month period in 2009, Spirit solar panels increased their power supply by over 60%. Cameras on the mast of the rovers document the cleaning. These cleaning events are one of the major factors in the extension of the mission time well beyond the original 90 days. The fact that the surface of Mars and the moon are dry and dusty will continue to be a problem for robots. In fact, Spirit and Opportunity went to Mars with a magnetic array to analyze the dust they were accumulating. The magnets attract charged particles, and those particles can then be analyzed by microscope and spectrometers on the rover's arm. For the Curiosity rover, which landed on Mars in 2012, engineers solved the dirt problem by removing solar panels altogether. For energy, they installed a radioisotope thermoelectric generator whose power comes from the steady decay of 11 pounds of plutonium-238. This nuclear power source was designed to last for at least 14 years and produce 4 times the amount of power produced by Spirit and Opportunity's solar panels. And you don't have to worry about the dust and the cleaning. Another problem that Spirit literally ran into was getting mired in loose, sandy sediments on the edge of a small crater. Spirit's final resting place is where it got stuck, at Troy in 2009. Getting stuck, however, permitted a wonderful scientific accident to occur. When engineers were attempting to get Spirit to drive out of the sediments, the wheels spun and threw material and churned up the surface. Doing much more than digging the rock that the abrasion tool could ever do, those wheels ended up being digging actuators, and they uncovered sulfates. Now, these minerals are formed in steam vents, and steam is usually associated with water. So getting stuck created a new perception-action link. The act of trying to drive turned into digging. That digging allowed new perceptions of buried materials. So the sad accident of Spirit getting stuck has actually resulted in one of its most important discoveries. Both Spirit and Opportunity had problems with their drive wheels, with one of the 6 getting stuck at an odd angle. So the adaptation was to drive the rovers backwards. Fortunately, the 2 wheels on the front and the 2 on the back can steer. What ultimately led to the demise of Spirit was power. Stuck in the sand, Spirit couldn't be maneuvered to angle its solar panels in such a way as to get enough light during the Martian winter to continue to charge its batteries to allow for communications. This movement problem was coupled with the gradual degradation of the performance of the batteries. Now, all rechargeable batteries slowly change, and even with a backup battery like Spirit had, you eventually have to pay the piper. Opportunity was able to operate for years longer because it was able to maintain its solar power. Towards the end of its life, Opportunity's flash memory began to wear out. The flash memory allows data to be stored when the rover is powered down. As we all know, using our computers here on Earth, sometimes memory or motherboards or screens just stop working. Well, perhaps in the future, a robot like Dexter will be on hand to repair or replace components when they break. As we celebrate the remarkable careers of Spirit and Opportunity, it's worth mentioning Lunokhod 1, the first robotic rover which landed on the moon back in 1970. Lunokhod, built by the Soviet Union, was the first mobile robot to explore an extraterrestrial body, and it returned hundreds of pictures and many tens of data points of soil samples. Given its success, Lunokhod's design was carefully studied by the United States in 1971, and we can see many of Lunokhod's design features in Spirit and Opportunity decades later. Multiple wheels, scientific instruments, and a radioactive source for heating electronics during the night. Lunokhod differed from Spirit and Opportunity in two important ways. First, its autonomous capabilities were fixed, not reprogrammable. Chief among those fixed capabilities were the operations of the scientific instruments. Second, Lunokhod did not drive itself autonomously, but rather relied on a human pilot working via remote control. As we place our robots deeper into space and farther away from our direct control, we will actually need them to be much more autonomous than they are now. And while we've seen that Spirit and Opportunity can be reprogrammed as their mission evolves, there's a limit to how much reprogramming can be done, and the delays only increase as our robots go deeper into space. So a likely alternative is to have the robots reprogram themselves. We call this process machine learning, and it's a field that's well developed in the highly structured environments where many robots work on Earth. So the challenge for robotics is to build learning systems for the highly unstructured environment of space. Soon I expect to see our robots learn as they go, fix problems they encounter themselves, and further extend our abilities to explore and work throughout our solar system.